All right, so the next set of slides is going to be about actor-critique algorithms. And this is essentially a way to synthesize together now the value-based techniques and the policy-based techniques that we've seen, because actor-critique algorithms will essentially have both a value function and a policy. Okay, so very briefly, we'll talk about, as a step towards actor-critique techniques, we'll talk about a policy gradient with a baseline. So this will help us to reduce, to speed up conversions. Then actor critiques, and then I'll come back to policy gradient, but now we'll discuss as well deterministic policy gradient, which necessarily have to be actor critiques because there we'll need to have a value function to make this work. Okay, so again, as I was mentioning, so as a quick recap, we talked about Q-learning. This is model-free, value-based. Now we also talked about policy gradient, which is model-free but policy-based, and then it does not have any value function. And now actor critique techniques are going to include both a value and a policy. And here the name comes from the fact that actor indicates that we are going to have a policy network to decide how we're going to act. And then critique means that we're going to have a value network that will tell us how good is the policy. So it will be a critique of the policy. Okay, so let's just quickly go over again the stochastic gradient policy theorem. So this theorem, we use it to derive those policy gradient techniques, in particular the reinforced algorithm. And then what's interesting is that this, this expression here has a Q function, there's the policy, and then there's also a stationary distribution. But then the expectations, which are those summations, are going to be dropped whenever we compute the gradient. Okay. Now, so this will give us a one sample approximation to the real gradient. Okay, but then this expression, we could modify it. It turns out that there's an equivalent notion of gradient that uses a baseline. So here, if I simply subtract from my Q function another function that I'm going to call the baseline function, and this baseline function is just going to be a function in terms of the states. It should not depend on the actions, just the states, and it can be any function in terms of the states. Then I can prove that this expression is the same as this one, or at least it's equivalent, because when I subtract B of S, what I'm effectively doing is now adding a term where I've got a summation with respect to A of the gradient of the policy times the baseline, right? So I'm effectively subtracting from here this additional term that corresponds to this. Now the question is, what does this term correspond to? Right? Because if this is really going to be equivalent, then this should be 0. And it turns out that it is indeed the case that it is 0, because I can rewrite this. So if I pull B of S in front, and then after this, I simply push my summation inside the gradient, then I get this expression. And now I can apply the summation to the distribution. Since this is a distribution, it must sum up to 1. And as a result, this summation gives us just 1. And then the gradient of 1 is 0. So this is pretty interesting because it means, again, that I can subtract some arbitrary function in terms of S from my Q function, and it doesn't change anything. So now, if that's the case, now an interesting question is there any advantage to maybe changing my gradient to work with a baseline like this, where I could subtract B of S from Q of SA? Okay, so it turns out that there are indeed some advantages. It's actually quite common to choose a baseline function that is going to be an approximation to the value function for a given policy pi. Now, if we use a baseline that corresponds to the value function, this is the expression that we get, so Q of SA minus V pi of S. And we can interpret this, and we can call that the advantage function. It's called the advantage function because here what we're really doing is simply trying to see the action, each action A, how much does it allow the Q function to get higher or lower than the value function with respect to a certain state. Okay, so here the value function, right, is assuming a policy pi. This policy is stochastic, so it will select every possible action, presumably with some probability, and take an expectation, right? So it's somewhere in the middle of those Q functions, but then some of those Q functions for certain actions are going to be higher, and some others are going to be lower. And then the advantage function is essentially just looking at, you see, how much the Q function differs from the value function. And then so the good actions are going to have a positive a positive advantage function, and then the bad actions are going to have a negative advantage function. And then it turns out that whenever we use the advantage function, it will allow us to converge faster empirically. Okay, so here the intuition is that whenever we do our gradient update, we used to do a gradient update that was based on the Q function, the Q estimate. No, I don't have this on this set of slides, but okay, so yeah, in the previous set of slides, right, when I explained the gradient update for policy gradient techniques, it was essentially the gradient of the log of the policy times G times gamma to the power of n, right? And then G was essentially the sum of the rewards starting in my current state with the current action, and then after that following the policy. So G was essentially a one sample estimate of my Q function. Now I'm going to replace my Q function, or that one sample estimate, instead by the advantage function. And whenever I do this, what it's effectively doing is that now you see the actions that are bad, they're going to have an advantage function that is negative, and then it means here that the probability according to this update should decrease, right? And then the actions that are good, then they're going to have an advantage function that is positive, and then their probability should increase, which is exactly what you would expect. Now, if we don't use the advantage function, but we simply use G as we had before, well, G would be the sum of the rewards. All the rewards might all be positive, and what we would effectively do is kind of increase the score of all those actions, and then we'd have to normalize, and then so it introduces more noise, more variance, and it takes longer to converge. Whenever we use the advantage function, then here we simply try to focus on what are the differences between the actions, and we just don't worry about trying to estimate well the level of the sum of the rewards for all of the actions. So essentially remove a good chunk of what would normally have to be estimated, which would create some noise, create some variance, and would take some time. So we remove that, and then we can converge more quickly. So that's the intuition. And then so here's the algorithm, the same algorithm that we saw before, the reinforced algorithm, but now with a baseline. And the difference is that we add or we modify those two lines here. So if you recall, whenever I use a baseline, then instead of having g, I'm going to have some difference of my Q function with respect to some baseline. And then so here I can simply do the update as follows. So I can simply measure, so this would be, if you want some estimate of the advantage function, because g is essentially the Q function, and then v is essentially the value function. And then so delta here is essentially a one-step approximation. No, sorry, it's a one-sample approximation to the advantage function. And then we can simply plug this in here. Now, to do this, we need to estimate what is the value function. And then we're going to have another network, so another neural network that will be parameterized by W. And then we can simply update it by using a gradient value update. Okay, so we saw last class how we can do an update using the gradient whenever we estimate a value function, either v or q. And so that's what we're going to use here. That allows us then to have an estimate of what is v. We can subtract this from our estimate of the q function, and this gives us an estimate of the advantage function, which we can plug in here. Okay, so this is then a better algorithm, and in practice, here's an example of the convergence rate that could be achieved on some problem if we just use the reinforced algorithm versus the reinforced algorithm with a baseline. Okay, so you can see that the one with the baseline converges much faster because, again, you see with the baseline we essentially remove a lot of the noise that has to do with just estimating the magnitude of all those rewards, and instead we focus on just the differences between the actions, so there's less noise to be captured, and then we can converge faster. Okay, any questions regarding this? Okay, so in practice, whenever you use a reinforced algorithm, in fact what you really want to do is use reinforce with a baseline as we just saw, and then so this would be the preferred algorithm that you would want to use. Okay, now if you look again at this code, what's interesting is that now this is not just a policy-based technique because we've introduced a value function. Right? So earlier we said that policy gradient techniques would only have a policy, and then if we simply use g, which is a one sample estimate of the Q function, then we'd never have to represent any value function, right? And then so it was a pure policy-based technique. But now once we introduce the baseline, it's not a pure policy technique anymore. So now we have both a value function and a policy. Okay, so since we're going to have a value function represented here, there are many ways in which we can estimate that value function. And then in the algorithm that I showed you, the value function is estimated through a Monte Carlo estimate. So you see, when I did the update for estimating my, my advantage function, I took g of n and then also my value estimate, and then yeah, that gave me my update. But here I have to wait till I have completed an entire episode, and this is really a Monte Carlo sample because I have to get an entire trajectory, and this is not sample efficient. So what is better in practice is to bootstrap by using a temporal difference update. So if we're really just trying to come up with a difference between the Q function and the value function, then here I could decide that, okay, I could simply, well, I guess this was an estimate of the Q function, or it could be an estimate of the value function if I select the action just based on my current policy. In that case, I don't have to wait till the end of the episode. I could just look at one reward and then use my current estimate of the value function to get something that would be equivalent to g of n. So this is something that's going to be faster, that's going to be more sample efficient. And then so here we would like to simply bootstrap from a temporal difference. And then this will have the benefit again of reducing variance and speeding up convergence. Okay, so this leads to what is known as an actor critique technique, because now what happens is that we have a temporal difference that is used to estimate the advantage function. And then we also have the value function that effectively evaluates how good the policy is. So yeah, so this is known as an actor critique technique because it has both. Now the previous algorithm that we just saw in Rich Sutton's textbook, it's not called an actor critique technique simply because even though there's a value function, the argument is that the value function does not critique yet the policy. So it's a very subtle point, okay? I don't know if we really want to argue about this, but in any case, this one is considered a proper actor critique technique because here the value function is really used to critique or to evaluate the policy, and then in turn it can be used to estimate the advantage function, and then we can do our update. Okay. So yeah, so here the way to think about this is that in this algorithm now, you see we are doing some value gradient update, right? So here the value function update is just a classic gradient update with respect to the value function. So this is a bit like if we were doing value iteration but using gradients instead. And now the policy update is a bit like policy iteration, but instead of literally changing from one policy to another in a greedy fashion, we do it through a gradient. So this algorithm actor critique, in fact, has some parallel with policy iteration techniques, because in policy iteration we alternate between evaluating a policy and then updating the policy. The difference is that now the way we evaluate the policy and update the policy is not by greedily selecting better actions or doing a Bellman backup, but instead is by taking steps in the direction of the gradient for the value function, and then in the direction that would improve the policy for the policy update. Okay, so you can think of this as really being a gradient version of policy iteration. Okay, so now, as we discussed, it's best whenever we do the updates to use the advantage function, and then in what I just explained before, when we introduce the notion of bootstrapping, so here I only use the value function as part of the bootstrapping update, but then if I really want to have a good estimate of the advantage function, perhaps I can use this update instead, where this is going to be clearly estimating the value function at the next time step, and then we've got the reward that might depend on the current state and action. So this will give us an estimate of the Q function, so that's our target. And then here we want to subtract from this now an estimate of the value function at the current time step. Now if we have a stochastic policy, then the value function can be estimated simply by taking an expectation of the Q function with respect to the distribution of the policy. Okay? So this is another way of computing the advantage. and then we can plug this in here, and then again this will converge faster. Okay? So I guess these are all slight differences that tend to increase convergence, and then in practice this is what you would want to use. And this algorithm now is known as the advantage actor critique technique. It's also known as A2C, and then in the literature there is an algorithm that became very popular recently called A3C, which is an asynchronous advantage actor critique. And then so it ended up being the state-of-the-art on Atari games. When it was proposed, then it was essentially following this, with the difference that some of the updates were done in an asynchronous fashion. Now it turns out that doing updates in an asynchronous fashion was not critical, and today people use a synchronous version, which is essentially this algorithm, and it's just known as the advantage actor critique, or A2C. Okay, so I guess, yeah, when you go out there and you look at different baselines or different algorithms, then you will see A2C that is often cited, and it's this algorithm. Okay, and then, yeah, the key is that it's an actor critique that uses an estimate based on the advantage function to do the update of the policy. Okay, now we've discussed so far how we can update a policy that is stochastic, but an interesting question is now, what if our policy, what if we want to have a policy that is deterministic? Because in many situations, having a stochastic policy is not something natural, and we'd like to make sure that when we're in a certain state, we're going to always execute the same action, so it should be deterministic. And then the reason why we consider stochastic policies was simply because whenever we make them stochastic and we introduce probabilities, then we can make the policy continuous. And that helps us in terms of deriving a gradient. However, if we already have a policy that is continuous, perhaps our state space is continuous, and then the action space is also continuous. So then this could simply be a function that is already continuous. So it turns out that we can also do gradient policy updates, but with respect to a deterministic policy, and then the gradient will correspond to this expression. So here I've got the deterministic gradient policy theorem. This was derived recently in 2014. And that's the expression. Okay, so it is different, but closely related to the stochastic policy theorem. The stochastic gradient policy theorem. Now, I'm not going to go through the derivation, but if you're interested, you can check out this paper. It has the derivation. And then you can show as well that if you have a stochastic policy and then you simply make it more and more deterministic, in the limit, this theorem will correspond to this one. Okay, so you can think of this as really being a special case of that theorem whenever we have policies that become deterministic. Okay, and then if you look at the expressions, right, so one big difference is that you see here the policy is stochastic because this is a distribution. Now here the policy is deterministic because the idea is that it's a function that takes as input a state and outputs a continuous action. Right? So that's why we don't see A here, but the idea is that when you compute pi of S, the output is going to be an action that's continuous, and then so this will be the expression. So in any case, we have the gradient with respect to the policy in both cases. But now a difference is that here we have an expectation with respect to, or at least a summation with respect to the actions of the Q function, whereas here we will have a gradient with respect to the Q function. Okay, so I'm not going to go into more details, but again, if you want to see the derivation, please have a look at this paper. Now, with this approach, we cannot have just a pure policy gradient technique that only has a policy and no value function, because we have here an expression that has the gradient of the Q function. Then it will be very natural instead to use an actor critique where we have a Q function represented explicitly, perhaps with a neural network, and then simply compute its gradient as well. Okay, so here's a deterministic policy gradient technique. In fact, in the literature, there's an algorithm called DDPG, which stands simply for Deep Deterministic Policy Gradient. And it's essentially this algorithm. Whenever you apply it to, in the context of neural networks, in other words, whenever your policy is encoded by a neural network, as well as your Q function is encoded by a neural network, then you obtain a deep deterministic policy gradient, but it's essentially this algorithm. So whether you work with neural networks or not, right, it's the same algorithm, and you're simply going to take some gradient with respect to whatever representation you have for your policy as well as your Q function. Okay, so the algorithm is very similar to what we saw before. This is an actor critique technique because it also has an explicit Q function and an explicit policy. And then we do updates for both of them. And then when we do the updates, you'll notice that you see here it depends on the gradient of the Q function as well as the gradient of the policy. But then here when we update the policy, it's both the gradient of the policy and the gradient of the Q function. Okay, so that's the main difference. Okay, any questions regarding this? Yes?
That's I think that's to update the part, to update the theta. It may need another set of iteration inside of this iteration, because that's we update the theta to modify that's the pi theta to a, and it is irrelevant to the updates of w, because w is we have the s and a. We modify w to fix the q. So I think that's this to update the theta is irrelevant to w. So it should be we use another set of iteration instead of this.
Yeah. Okay. Very, very good point. So here you're right that the updates for q are somewhat separate from the updates for pi, but you see in the update for pi, right, we need the Q function. Okay, so here we need the Q function, and in fact we need to be able to take the derivative with respect to the Q function. Okay, so that's why the two will work together, but you're right that here we could do multiple updates to the Q function before we start doing updates to the policy. And again, this would correspond to modified policy iteration, where in modified policy iteration, you do several updates to your Q function, and then you do an update to your policy.
No,
so here I'm just showing for one update.
No, what I mean is that we can do multiple updates for the pi, then go back to the iteration of the.
Oh, sure. Yeah, we can also do multiple updates to pi, because here when we do these updates, these are gradient updates. So the idea is that we are measuring, or we are computing a direction in which we should do an update, and then we take a small step in that direction. But then when we take a small step in that direction, that might not be enough. And in general, all techniques for optimization that rely on a gradient, you need to take multiple steps, right? They're iterative techniques. So you're absolutely right that here, the update for pi, we could do multiple updates for pi, so have an entire loop here before we get back to doing updates for q and so on. Yeah. Yes?
I just want to compare this algorithm to the deterministic gradient policy theorem. Like, before you have some expectation over all the space, right? But here you don't have the expectation. I'm wondering why.
Ah, yes, good point. So here we have an expectation in the theorem, and then when we do the update, right, then here the expectation is gone. The idea is that this is an estimate of the full gradient, right? So normally we should take an expectation, but then in the algorithm, we can't compute this expectation because this expectation depends on a distribution. This would be the stationary distribution of the policy that is not easy to compute and would also require us to know what is the distribution, the transition distribution based on a model and so on. So in practice, what we do is we approximate this expectation with one sample. Right? So really, I guess here I've got the exact gradient, right? And then in the algorithm, what I'm doing is applying the gradient, but applying a one sample approximation to that of that gradient. So we're really doing stochastic gradient descent.
Can we achieve faster convergence by adding more samples?
Yes, very good point. So yes, so here there's an interesting question about, since we are really approximating the expectation with one sample, perhaps that's a crude approximation and we might want to approximate this with multiple samples, right? So then before we actually update theta, we might want to compute this for multiple state actions and next state triples, right? And then add them together, which would give us a better estimate of the full gradient. Now in practice, that doesn't usually pay off. So that's why it's quite common to, whenever people do stochastic gradient descent, they will approximate the gradient with a single sample, because the next update you do, which is again just a one sample approximation, even though they're asynchronous, you can think of them as almost being synchronous. The only difference is that you see here, you update theta before you compute your next sample, right? And then when you update theta, perhaps you actually make a step in a good direction, so you actually make progress, and then you might as well compute your next gradient based on that better estimate. Now this is not always the case, because since here the gradient is computed based on a single sample, it's possible that your single sample is a crude estimate that makes you go into a bad direction and then you make things worse. But in practice, most of the time, right, you actually do go in a good direction, and then as a result you improve, and then it's better to simply do the improvement and then compute the next gradient with respect to that improved policy. So empirically, at least, this is what people have observed, and then it's not just in the context of reinforcement learning, but all of machine learning, right? When people use stochastic gradient descent, then they often do this with respect to a single sample.
But
Yeah.
there's no formal proof for this.
Right, is there a formal proof for this? I'm not entirely sure, okay? So I'm not an expert on that topic. There's actually a whole community studying how to come up with better gradient descent techniques that might use mini batches or various schedules, and then so yeah, I'm not entirely sure. So there might be some formal proof of when this is beneficial, but I'm not entirely sure. Yeah. Yes.
The implementations of DDPG that I've seen all have a replay buffer, so they would use a batch to update.
Yes, okay, very good point. So yeah, so here I'm not showing any replay buffer, I'm not showing any target network, but you're right that yeah, in practice, DDPG and in fact all the other algorithms for actor critiques that I showed before would all use a replay buffer and a target network. Okay, so here I just wanted to keep things simple. So the replay buffer would essentially mean that we have some loops, especially with respect to the Q function, and then yeah, there would also be a target network But then it would follow the same as what we've seen in the context of deep Q networks. Yeah.